now we have the general statement of Gauss's law, and as I mentioned in a previous video, this can be a very intimidating result to apply because of surface integrals and volume integrals. But we will look at sources. So we're going to look at sources that are what we refer to as symmetrical sources. And for these three categories of sources, to apply Gauss's law will be a bit difficult, but much easier than you might imagine right now. And our three sources, the symmetries that we're going to talk about, are spherical symmetry. And what's crucial with that is let's draw a source. Here's some charge density rho. It's not a point charge. And the fact that there's spherical symmetry means that the electric field, and if this is positive, is pointing away from the source. And on any spherical surface, the magnitude of E will be the same. Now, the second type of source is something that we refer to as cylindrical symmetry. And here, we imagine we're actually going to look at infinite cylinders. So I'll just draw that schematically as our source. And if, again, now we can either refer to this if it's solid, there's a charge density rho. And for this infinite type of cylindrical source, again, because we're drawing arrows, let's make rho positive, then the axis of symmetry here is along the central axis. And one way we have an electric field that points radially away from the axis of symmetry. Now, you might ask, well, why the word symmetry? And one way to imagine it is that if I took this cylinder, where you have an electric field that's pointing radially away from the axis, you closed your eyes, and I rotated this cylinder, the electric field would still be the same because you couldn't tell when you opened your eyes again that I rotated the cylinder. And the only type of electric field that doesn't change when you rotate it is an electric field that's pointing radially outward. And that's how, in physics, we sometimes use what we call symmetry arguments. Now, our third source, and I'll make that down here, our third source has planar symmetry. And again, what we'll look at is an infinite plane. So I might have a source, and it could be some type of volume. This is an infinite plane with a charge density rho. And now, with this type of source, because it's infinite, you could imagine that I could take two little pieces here and there, and if I looked at the line dividing them, then the electric field, call this 1, the electric field 2. And when you add them together, you get some total that is only pointing perpendicular from the plane. And so what we argue is that if the plane were infinite, everywhere outside this plane, and now I'm going to draw that plane like this, seen on edge, that everywhere outside this plane, the electric field is pointing perpendicular to the plane. Now, this type of pairwise argument to cancel components that are not perpendicular, you could try yourself to see if you could apply a very similar pairwise argument to this cylinder to conclude that the electric field is pointing radially outward. Radially away. When I say radially outward for the cylinder, I mean radially away from the central axis of symmetry.